So I welcome you to my talk, show you how to nest numerical algorithms. It's about the problem which you see animated here. A red rigid body is suspended from the ceiling on 3 blue wires, rigid wires. It turns. Doesn't look like a smooth animation to me, but anyway. So you turn the red body, the wires lift up the body, there's a return torque, and the thing starts to oscillate. And the practical problem which I'm dealing with, still like a toy problem to demonstrate this ability of Mathematica, but the problem is that I want to know the moment of inertia of that red rigid body which is rotating here. I want to obtain that from the period. So I'll set up the equation of motion and I'll calculate the period from the inertia. That's the numerical solution of a differential equation. That will be the inner numerical function. And that gives me the periods in terms of the inertia. And inverting that will give me the inertia in terms of the period, and the function inversion, numerical inversion of that numerical function Z. That's the outer numerical algorithm. And that's something which you need really from time to time, this kind of nesting, and it runs really nicely in the Wolfram language. First of all, I thought you, whoops, that was one too many. You would also be interested in the company I work for and in myself. So I work for Continental, the automotive supplier, or you may know us for our tires. But we also make all sorts of automotive parts, in particular brake systems. That's a brake controller, that's a brake booster, and that's more what I work in. Tires is 1/3 of the company. Other automotive parts are 1/2, and brakes are actually a significant portion of that, 5 or 10% overall. It's a large company with over 40 billion euro sales and about 200,000 colleagues last year. And we are working all over the world. And now to narrow a bit down to the brakes and driving dynamics and safety business area which I work in, this gives you an impression of what we do. So these are the brake controllers, which is actually where I am most involved. Then there are the actual wheel brakes, hydraulic or electric brake boosters, sensorics, airbag control units, quite a different important thing, air suspension, modern stuff like these autonomous mobile robots, which we're interested in for our own purposes, but also to get into autonomous driving. So already my corner of Continental is quite interesting. I myself did mathematics and physics at university. It was rather pure mathematics. Always worked on the classification of things by degree of continuous symmetry. I did my diploma at Darmstadt in 95. My PhD at Stuttgart in 99, and also habilitation at Darmstadt in 2004. And then I immediately joined Continental and have developed electronic brake systems since then. I started in component simulation, finite elements for electromagnetic valves, motors, things like that. Then I moved into system simulation for the entire brake control system. Brake control means anti-lock brake system, electronic stability control, and related stuff. So I'm responsible for providing models of the physics of all that. And from the simulation point of view, I've also very much worked on system design for integrated brake systems, where the brake pedal actuation, the pressure generation, and the anti-lock brake system are all in one unit. That's a rather modern development. Right, so back to that example problem and to the abilities of the Wolfram system. As I said, I want to, let's see whether the animation runs smoother now. Maybe a bit, but not terribly. So I want to observe the rotation in order to measure the inertia, and oh, this doesn't stop playing. Oh dear. Whatever can go wrong will go wrong. So first thing is to understand the geometry, and so I'll try presentation mode later, but first of all, what I need to show you is that you start with some geometry. Yeah? So you have the angle, and you want to calculate the height from the angle, and that's this formula. And that's elementary geometry. The blue triangle here is a right-angled triangle. So you have something like Pythagoras, which you see here. And then you actually have sine of phi over 2 squared, which then is transformed in some way into the cosine of phi. You'll believe me that something like that is possible, and this is the formula which comes out. I'm not evaluating everything now. Right, so there's a height constraint in terms of the wire length L and the radius R of the red body and the angle phi. And I'll do things numerically, so I'll introduce default parameters like a mass of 500 grams, a length of 1 meter, etc. And the energy is the basis of everything. I'll risk it and start presentation mode once more. Seems to run better than last time. Right, so the energy is rotational energy, kinetic energy, plus the kinetic energy of the vertical motion, plus the potential energy of the height, where the height is at the time being some function of the angle. And the equation of motion is derived from conservation of energy. So that's the basic thing. Yeah? Time derivative of energy vanishes. We also want to solve that for the angular acceleration because we want an explicit differential equation. That's about what it looks like. Must not forget to actually do that. All right. So, and if I actually use the constraint height, that is some complicated formula that doesn't really matter. What I find interesting is that when you develop that for large wire lengths, then you get, that's the right-hand side, yeah, that's what the angular acceleration is equal to. Then you get something in terms of sine, or more precisely, minus omega 0 squared times sine. So an ordinary mathematical pendulum. And if you don't do that approximation, then you also have an explicit expression which is more complicated. And now I want to obtain the period from that. So what's that? That can be solved. I already plotted the numerical solution here. I start from a certain angle at speed 0. And then I follow that over time, and the period ends when the speed crosses 0 again. So this is how you get the period for the default parameters plus a specific moment of inertia j with initial position 90 degrees and 0 speed. And a when event detects that the speed goes through 0 from above. And then I print the time and stop the integration. Right. And I'll put all that in a function, which I can then evaluate for different inertias and different initial angles. Function contains in the center really what I showed above, but now the time is not printed, the period is not printed, it's assigned to a variable and returned. So when I evaluate that function with the same inertia and angle as before, I get the same period as before, but now I can also let one parameter run, for instance, the initial position. Notice that in this nonlinear oscillation, the period depends on the initial position. And the other thing is I can run the inertia. So now I get the period for all inertias. And now I said what I want is a measurement principle for the moment of inertia from observation of the period. So say the period is 2 seconds, which I observed. Which moment of inertia does that correspond to? So you go into that graph and find that it's about 1.43. Or of course you want to do that algorithmically and numerically. Yeah? So you have the period function, which I just defined. And you want that to be a prescribed value by varying the inertia. So that's the find root around everything. And that's the point. Here ND-solve is disguised in period and nested within find root. There's the period wrapper function, and I forgot to emphasize that is only evaluated for numerical arguments. You check for both arguments and don't try to evaluate with a symbolic value. You wait for both the moment of inertia and the initial angle to be numeric. And that is crucial here. That only works because find root cannot try any symbolic evaluation. So the wrapper function is an important ingredient. Then I found in many such examples that it is that the inner numerical function presents something like numerical noise, and so the outer tolerances should be relaxed. If the period has some random or pseudo-random fluctuations in the order of magnitude of, I don't know, 10 to the minus 8 or so, then to only require a solution up to 10 to the minus 6 is certainly a reasonable thing to do. Interestingly, in this example, it did work without relaxing tolerances, but in other examples, which I tried in the course of the years, that was really important. Other examples, such as an optimization, which is convex in most variables and nonlinear in a few. And then you do the convex optimization as the inner optimization problem, and then you nest the find minimum around that. Or there is another example in a Wolfram University course on advanced numerical algorithms, which I linked here. So you can do that. It works really fine. Also notice how fast it worked. And yeah, it just works if you plug things together in that way. And that's a really nice observation, which I believe can be useful in many contexts. And of course, one nice thing is that it can be put into manipulate and then deployed. So these numbers are the example which I started with. And this, I gave something like that to colleagues from our test department, who can then put in the exact mass and the exact things they measured and period they observed, and they will get a result here. And of course, possibly a result with a nice animation or graph or whatever. So the deployment is also built into Mathematica. And this thing here is easy enough to run in the Wolfram player. It's all one manipulate only. Right. So a small observation which I found neat and useful. And I think I'll stop very soon here and would like to discuss. I would like to say that I prepared a few slides about possible questions as appendices here. So first of all, we could explore the long wire approximation a bit more. The inner numerical algorithm for this particular problem could be a numerical integral rather than an ND-solve. And this may also call for other Wolfram language functions. For instance, if I vary just one parameter in ND-solve, parametric ND-solve can be used. And also the 14.1 brand new functions for finding fixed points of differential equations. They can also be applied here. So all this is stuff which we could discuss. What I want you to take away is that this nesting of one numerical algorithm inside another is something which are often used, which often worked routinely with just a few tricks. One thing to know is that a wrapper function which delays evaluation until numeric parameters are provided. And the other thing is the relaxation of the outer tolerances. Actually, I had one example where the inner algorithm used software precision, 30 or 50 digits or so. So the inner algorithm sometimes needs to be very precise. The outer algorithm needs to be relaxed. And if you use these tricks, yeah, you can often do it, plug one thing into the other. Thank you very much, and I'll now check the questions. While you think of questions, I'll of course go to my appendices. I'll start from the end. D fixed points is a function in 14.1, and it does work here. Yeah? So you try it on the toy example first. It gives the fixed points. It also tells you that the one where the pendulum, if you think of this as a pendulum, where the pendulum is hanging down, that's stable, and the one where the pendulum is pointing upwards is unstable. Same works for this much more complicated equation with the complicated right-hand side. It didn't work for all the parameters at the time, but here, for instance, where the most of the parameters were numeric, only the moment of inertia was symbolic. yeah, it did give the correct solution here. A stable fixed point at 0, 2 pi, 4 pi, etc., and an unstable fixed point in between. And then maybe the thing about parametric ND solve. One interesting thing about that is that it didn't quite work because I didn't understand the mechanism, which is described here without the help from Oliver Rübenkönig. So you can prepare the solution of an ODE with open parameters. That's parametric ND solve. And then only vary the moment of inertia, say. And what I did was I sewed out of the when event. And that was unstable because I didn't understand about caching. And now you can turn off caching and then everything works. I don't think it's not so insightful to go into the detail here. You would just do a parametric ND solve with open inertia, so then the wrapper function, that period function, becomes simpler, and the process becomes a bit faster, not much faster in this simple example, but in other examples it may be more important. And I was not aware that events work also in parametric ND solve. I mean, depending on the parameter, the time interval varies, and I think it's not obvious that that's working, but it's working again. It's in another example that the whole system, just works when you plug things into each other. That's also nice to see. Now, I still don't see any questions. And time's about up. So I'll switch back to my takeaway. And hope that you enjoyed the conference as much as I did, and that you enjoyed the last 1 or 2 talks. Thank you very much.